Today, we're going to start building up a set of rules for finding derivatives. This is in the cleverly titled chapter, Shortcuts to Differentiation, or how to avoid all that algebra. So far, we've been finding the derivative by applying the definition of the derivative. The reason for that is we want to emphasize that the derivative is giving us the slope of the line tangent to a curve at a given point. That's why it's the limit of a secant line where the points are getting closer together. The h is how far apart the points are, and we want that distance to go down to 0 to make a tangent line. But now we want a more mechanical thing. We want to be able to find derivatives without having to use the entire definition of the derivative to do it. So today we're going to start introducing some shortcuts to differentiation. And we're going to start with the big one. So the derivative, not going to mess around with this, the derivative with respect to x, I'm going to use Leibniz notation. So this notation, d over dx, means take the derivative of whatever comes next. So the derivative with respect to x of x to the n is equal to nx to the n minus 1. So writing d over dx in front of a function is an instruction that says, take the derivative of the function. So this symbol it means take the derivative with respect to x. That's the dx on the bottom. And what that means is that x is the variable. So when we say with respect to x, we're identifying what the variable is. So that's the symbol d over dx. And we'll just say d dx of x to the n. And it just means take the derivative of the function. What we have here is a simple rule for taking the derivative. The derivative of x to the n is nx to the n minus 1. You multiply by the exponents, then subtract 1 from the exponents. So first you multiply by the exponents. And then you subtract 1 from the exponents. You multiply by the exponents, then subtract 1 from the exponents. The reason I label this as a two-step and label step 1 and step 2 is that eventually we're going to want to invert this process. And so when we invert something, we do the inverse operations in reverse order. So we will subtract 1 from the exponents, with add 1 to the exponents, and then we will invert multiply by the exponent with divide by the exponent, and we'll do that in the reverse order. So we'll perform inverse operations in reverse order. All right. Let's do some examples. It's death by examples today. Let's find the derivative with respect to x of x to the 5th. Type in the chat the derivative of x to the 5th. Five x to the 4th. We multiply by the exponents, then we subtract 1 from the exponents. And this is the derivative of x to the 5th. The nice thing about this rule is that it is super useful. If we can write things as powers of x, then we should write powers of x. For example, let's suppose I wanted to find the derivative of the square root of x. What's another way we can write the square root of x? What is the square root of x where x is raised to a power? We can look at this as x to the 1/2. And then we can just apply our rule. We multiply by the exponents and subtract 1 from the exponents. If we can write powers of x, then we should write powers of x.
Can you explain again how you got to 1/2 on the exponent?
Yeah. A square root is a 1/2 exponent. Whenever we have the nth root of x is a 1 over n exponents. The index of the denominator, the index of the radical is the denominator of the exponent. It must be this way because if I take a square root of x and then square it, I'll end up with an x to the first. So if I take a square root of x, we know that a square root of x squared is equal to an x, and this is to the first power. So this must mean that if we raise x to a 1/2 power, since when we raise an exponent to an exponent, we multiply the exponents, it must mean that a square root of x is a 1/2 power. So this is why we say that the index of the radical is the denominator of the exponent. The index of the radical 2 is the denominator of the exponent, 1/2. So if I have, for example, the derivative of the cube roots of x, the index of the radical is a 3, so this is the derivative of x to the 1/3 power. So we multiply by the exponents and subtract 1 from the exponents. The index of a radical is the denominator of the exponent. So we can combine this with other things. If we see radicals, we can write them as fraction exponents, which is better anyway. Radicals are an archaic, weird notation. I like fraction exponents better. Let's suppose that we want to take the derivative of 1 over x to the 3rd. Once again, we can think of 1 over x to the 3rd as x raised to some power. How would we rewrite 1 over x to the 3rd as x raised to a power? What should we write this as? This will be x to the -3. So the exponent is just a -3. So now we can apply our rule. We multiply by the exponents and we subtract 1 from the exponents. Careful that when you subtract 1 from -3, you go to -4 and you don't add 1 to the exponent and end up at -2. A very common mistake. So an exponent in the denominator will be a negative exponent in the numerator. This makes sense because if I have 1 over x to the 3, I know should cancel out with an x to the 3rd. So if I write 1 over x to the 3rd, and I multiply that by x to the 3rd, we know that this will cancel out to 1, or x to the 0 power. We also know that when we multiply things with the same base, we add the exponents. So it must be that this 1 over x to the 3rd is an x to the negative 3 power. Because when we multiply things with the same base, we add the exponents. Negative 3 and 3 will make x to the 0, which is where the 1 comes from. So the x to the 3rd cancels out in the numerator, cancels out with an x to the 3rd in the denominator. So we multiply by the exponent, subtract 1 from the exponent. We can even apply this, both of these rules. Let's suppose that we wanted to take the derivative of 1 over the square root of x. What's the exponent on the x in this case? We want to write this as x to some power. It's a square root, so that means a 1/2 exponent, and it's in the denominator, so that means we'll make it negative. So it's going to be an x to the negative 1/2. Our derivative rule is multiply by the exponent, multiply by a negative 1/2, and subtract 1 from the exponents. So negative 1/2 minus 1 is negative 3/2. Quick thing to be really careful of. If we wanted to write this in a single line, if we want single line syntax for this x to the negative 1/2, if we write x to the negative 1/2, if we try to tell a computer or a calculator, if you try to use this expression in a computer or a calculator, it's going to read as x to the negative 1, and then it's just going to divide by 2. So this, just typed this way, will be read as x to the negative 1 and then divided by 2. So this is how the order of operations would apply to that expression. If we want to make sure that we have the negative 1/2 as the whole exponent, the divided by 2 is part of the exponents, then we would want to write this as x to the exponent, x to the parentheses negative 1/2. So this says take the negative 1 divided by 2 and then make that the power of x. Make that the exponent. So this is the one that we want, just typing in this case. So be careful with parentheses. So if we're writing things on a single line, like we would be in a text message, or if we're typing out an email, we've got to be really careful with our parentheses to make sure that we're clear in our communication. In this case, I knew that you wanted the negative 1/2 to be the exponent, so I didn't worry about parentheses. But if we're going to try to talk to a computer and not a human being who knows the context of the question and knows what the point is, then we're going to have to be more clear in our communication. Remember, computers are very, very dumb, and they will take things literally. When a computer reads something literally, they don't think it's going to be used for emphasis. They are just going to read things literally. A human should know better. A human should know that if you say that I was literally dying, you know you're just trying to emphasize the fact and you are not meaning that you were literally dying. And anybody that says otherwise is just not playing the language game. That's not how this works. Plus, that's going to make that call had better not cite Shakespeare as a master of the English language. Because, I mean, you're clearly just not understanding how this works. You know what I mean? It's like when you ask a teacher, can I go to the bathroom? And they're like, well, I don't know, can you? And the student should be like, the student with the proper amount of sass would be like, oh, you know what I meant. I'm going to the bathroom. Or the super move, if you're a student and you're like, oh, can I go to the bathroom? And the teacher says, I don't know, can you? If you really want to drive the point home, go ahead and pee in your pants and then be like, oh, yes, I can. That's the power move. Or if everything's going to be literal, when the teacher's like, oh, I don't know, can you get up, walk out to the bathroom? When you come back, be like, oh, yes, I can. You know what I mean? Power move right there. And if they criticize you, be like, oh, well, you asked me a question. I just did science to find out. I ran an experiment to find out. And my original assertion was correct. I had a theory and I tested it. So what are we talking about? Oh yeah, we're talking about finding derivatives. Be careful with your parentheses. When you type this in the chat, I know what you meant, but a computer is definitely not going to know what you meant. And so the computer is just being like your little brother. It's like, I'm not touching you. And computer's going to be like, oh, that's not what you wrote. You wrote this. Computers are dumb. Look at all the work we have to put into them just so they can mimic a fraction of our power. All right. Let's start. Test how well you can guess at things. Let's suppose I want the derivative of x to the fifth plus x cubed. What's the derivative of x to the fifth plus x cubed? So with this example, some of you were guessing 5x to the fourth plus 3x squared. There's two different terms. Can I just do the derivative of each term separately? And the answer is yes. It works exactly how you would guess that it works. We could summarize this by saying that the derivative of a sum is a sum of the derivatives. So the derivative of a sum is a sum of the derivatives. The derivative of a sum is a sum of the derivatives. So if we have multiple terms, we can just deal with those a term at a time. Even if we're combining them with the other rules. So if we have, say, the derivative of the square root of x plus 1 over x to the third, I can just write this function with powers of x and say this is the derivative of x to the 1/2 and write the x to the 1 over x to the third as x to the negative 3, and then just take the derivative a term at a time. The derivative of x to the 1/2 is a 1/2 x to the negative 1/2. The derivative of x to the negative 3 is negative 3 x to the negative 4. And we should recognize that we are avoiding a lot of algebra by using this rule. We should also recognize that you're all taking my word on how that this is how it works, but feel free to disagree with this as a rule. So the derivative of sum is a sum of the derivatives. Let's change things up a little bit more. What if I wanted the derivative of 7x to the 5th? So instead of just the derivative of x to the 5th, what if I wanted the derivative of 7x to the 5th? What we might be guessing is that we just multiply the result multiply the derivative of x to the 5th by 7, and you would totally be correct. The derivative of 7x to the 5th is 35x to the 4th. The derivative of a constant times a function is that constant times the derivative of the function. Derivative of a constant times a function is the constant times the derivative of the function. So the derivative respects addition and scalar multiplication, multiplication by constants. The derivative is a linear operator. The derivative is what we can call a linear transformation. It respects addition and scalar multiplication. That's a bit of DVD bonus material, and if I edited my videos, I would probably edit that part out. And the actor that played this role would just not end up in the credits. But in the director's cut, that scene is still there. It's like a deleted scene. And I released the director's cut after you've been in linear algebra, after Calc 2, and you're like, well, hey, I remember. Leach mentioned in the first film that the derivative is a linear transformation. I didn't know what a linear transformation was then, but I know now. And all the classes start connecting together. All right. Some things that don't apply. The derivative is a linear transformation, which means the derivative of a sum is a sum of the derivatives. The derivative of a constant times a function is a constant times the derivative of the function, but the derivative of a product is not the product of the derivatives. If we want to find the derivative of a product, let's suppose we wanted to find the derivative of x squared times 3x minus 7. In this case, the derivative of a product is not the product of the derivatives. But in this case, we can rewrite this expression as terms. So since this is not a big deal for the multiplication, we just multiply this out with the distributive property. And I can say this is 3x to the third minus 7x squared. And now we can use our simplified rules. 9x squared minus, the derivative is 9x squared minus 14x to the first. Also, if, for example, we had to find the derivative of, let's say, 3x minus 7 squared. Now we have a composition of functions. We can just use some algebra to simplify our expression. So I can rewrite 3x minus 7 squared, or I can rewrite the square of the difference between 3 times a number and 7 as 9x squared minus 42x plus 49, and then take the derivative by terms. So we'll have 18x minus 42x to the 0. The 49 is a constant, so we can read that as 49x to the 0, and so the derivative is 0. The derivative of a constant is equal to 0. I'm supposed to save that as a surprise for your homework. So spoiler alert. The derivative of a constant is 0. This makes sense because I can read 49 as 49x to the 0 power. So I multiply by the exponent and then subtract 1 from the exponent. It'll be 0x to the negative 1, and that'll just be 0. Any questions? All right. What we want to remember is what we refer to as the big one, or the power rule. The derivative of x to the n is nx to the n minus 1. We multiply by the exponent, then subtract 1 from the exponent. Since the derivative is a linear transformation, if we can write terms with powers of x, then we should write terms with powers of x, and we won't need any fancy rules. Any questions, comments, or snide remarks? All right, so there is a new homework assignment. Chapter 3, section 1. It focuses on this power rule, nx to the n minus 1. The derivative of x to the n is nx to the n minus 1. You just have to practice that so that we can go on to find derivatives of more complicated things. Any questions, comments, deep thoughts? All right, that's going to do it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.